Now that we're done with this module, that concludes Unit 8. So we'll summarize a little bit, not just from this module, but all the modules that are in Unit 8. The focus of this module, Inference for Means, is inference for a population mean, or a difference between two population means. We begin this module with a discussion of the sampling distribution of sample means. We then develop a probability model based on this sampling distribution. We use the probability model with an actual sample mean to test a claim about a population mean in a hypothesis test, or to estimate a population mean with a confidence interval. We then move to inference for a difference in two population means, or a treatment effect. Now we'll talk about sampling distribution of means. If we have a quantitative data set from a population with mean mu and standard deviation sigma, the model for the theoretical sampling distribution of all random samples of size n has the following properties. First, the mean of the sampling distribution is the mean mu. The standard deviation of the sampling distribution of means is sigma over the square root of n. Notice that as n grows, the size of our sample, the standard error of the sampling distribution of the mean shrinks. That means that the larger samples give more accurate estimates of the population mean. Thirdly, for large enough sample sizes, the sampling distribution of means is approximately normal, even if the population is not normal. This is called the central limit theorem. If a variable has a skewed distribution for individuals in the population, a larger sample size is needed to ensure that the sampling distribution has a normal shape. Also, the general rule is that if n is at least 30, that's kind of the magic number, then the sampling distribution of means will be approximately normal. However, if the population is already normal, then any sample size will produce a normal sampling distribution. We practice finding a probability associated with a range of sample means, which is similar to finding a p-value in hypothesis testing. The process is as follows. First, convert a sample mean x into a z-score. But now the z-score is a little different than it was before, because now we're looking at the sample mean. We said the sample mean can be approximated by the population mean mu, but the standard deviation is not sigma anymore. It's sigma over the square root of n. So we have to add kind of a little square root of n in the denominator's denominator to make it fit the new idea that we're talking about now, because now we're looking at samples. Okay, and then from there, once we calculate the z-score, we use technology like a calculator or some website or an applet like we see, or StatCrunch, to find a probability associated with a given range of z-scores. We also then talked about confidence intervals. A confidence interval approximates a population mean by giving us a range of values that likely contains the population mean mu. The general form of the confidence interval is x plus or minus the margin of error, or in other words, that's equal to x plus or minus the critical value times the standard error. We covered the following different types of confidence intervals. The one sample z interval that formula would look like this: x bar plus or minus the z-score for that critical value times the standard error would be sigma over the square root of n. And then the one sample t interval, it's almost the same, but the only difference is you're using a t value for that critical value instead of a z-score. And then also the numerator of that fraction is s, the sample standard deviation, rather than sigma, the population standard deviation. Now we'll look a little bit more on the t value specifically here, or the t model, sorry. The t model, when the standard deviation of the population is unknown, which is often the case, we use the t model to find the critical values. When using the t model to find critical values, we need to select an appropriate number of degrees of freedom. In the one sample case, the number of degrees of freedom is one less than the sample size. Degrees of freedom equals n minus 1. In the two independent sample case, the degrees of freedom come from the complicated formula, and we often use technology to find the degrees of freedom in that case. Our conclusions: we say we are 95% confident that the population mean falls within our confidence interval. That really means that about 95% of all confidence intervals computed in this way will capture the true population mean. Now our conditions: the population must be normally distributed, or the sample size must be large enough. The magic number, like we said, is 30. N must be at least 30 or greater than 30 in the case of the two sample t interval. Both populations or samples must meet these conditions. In practice, we use t procedures with smaller samples if the distribution of the variable in the samples is not heavily skewed and is without outliers. We take this as an indication that the variable has a fairly normal distribution in the populations. Now we talk about observations for confidence interval structure. First, as we saw with other confidence intervals, the width of a confidence interval is twice the margin of error. The smaller the margin of error, the narrower the confidence interval, and the more precise the estimate of the population parameter. Second, increasing the confidence level decreases the precision. The larger margin of error, so a wider interval. Decreasing the confidence level increases the precision. A smaller margin of error means a smaller or a narrower interval. Thirdly, confidence intervals are useful estimates only when they provide a good balance of confidence level and precision. In order to increase precision without losing confidence, we must increase the sample size. In other words, larger samples provide more precise estimates without sacrificing confidence. Now we'll look at hypothesis test for statistical significance. Okay. The process for any hypothesis test consists of 4 basic steps. Define the hypothesis, that's the first step. Second, collect the data. We need random samples that are representative of the population. For the 2-sample t-test, the samples must be independent. 3 would be assess the evidence. Assessment includes checking appropriate conditions, computing test statistics, and finding corresponding p-values. Fourth, the last step is to state the conclusion. We compare the p-value to alpha, some significance level that was given or understood at the beginning of the problem. We decide whether or not to reject the null hypothesis, and then we'll state the conclusion in context. Specifically, the null hypothesis gives the value of the parameter we use to create the sampling distribution. In this way, the null hypothesis states that we assume to be true about, or states what we assume to be true about the population. And then on the other hand, the alternative hypothesis, H sub A, usually reflects the claim in the research question about the value of the parameter. The alternative hypothesis says that the parameter is greater than or less than or just not equal to the value we assume to be true in the null hypothesis. When the alternative hypothesis is that mu is less than the null mu, or the given mu that was in the null hypothesis, or that mu is actually greater than that, the test is called a one-tail test. For the paired t-test, the alternative hypothesis would look like mu is less than 0 or mu is greater than 0 in the case of the one-tailed test. For the 2-sample t-test, the alternative hypothesis would look like 2 mu's, one population mu minus the other would be negative because one's bigger than the other, or the other way around. The 2 population mu's or means would be, the difference would be positive because the first is larger than the second in the case of the one-tailed test. Now, in the alternative hypothesis, instead of being a one-tailed test where mu is greater than mu sub 0 or mu is less than, it's just, let's just say they say it's not equal to, then the test is called a two-tailed test because I have to account for mu being less than mu sub 0 and also mu being greater than. For the paired test, the alternative hypothesis would look like mu is not equal to 0 in the case of the two-tailed test. For the 2-sample t-test, the alternative hypothesis would look like the 2 mu's, the population means subtracted, would not equal 0 in the case of the two-tailed test. Now we'll look at conditions here. The conditions that must be satisfied in order to carry out a t procedure are as follows. First, the population is normally distributed or the sample size is large, at least 30. This applies to both populations for the 2-sample t-test. The samples must be random in order to avoid bias. And thirdly, the samples must be independent in the case of the 2-sample t-test. Now the test t statistic is given by this formula, the sample statistic minus the hypothesized parameter all over the standard error. We've learned about 3 different types of t-tests. So the one sample t-test here, then you use this formula, t is equal to x bar, so the sample mean minus the mean that was given in the hypothesis test, in the null hypothesis over the sample standard deviation divided by the square root of n, which is the sample size. In the paired t-test, however, it's a little different because mu sub 0, we're thinking of it as 0. We calculate the differences, then find the mean of the standard deviation. The 2-sample t-test, that's the complicated formula that we said we never really have to do by hand, that we'll just use StatCrunch for. So don't worry too much about that formula. We won't have to use it. But p-values now. The p-value is the probability of finding a random sample with a test statistic at least as extreme as ours, assuming that the null hypothesis is true. We find p-values by using the t-distribution. To come to a conclusion about the null hypothesis, we compare the p-value to the significance level alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis and conclude that there is significant evidence in favor of the alternative hypothesis. If p is greater than or equal to alpha, we fail to reject the null hypothesis and conclude that the sample does not provide significant evidence in favor of the alternative. And then lastly, we talked about two different error types. Hypothesis tests are based on random samples, so the conclusions are really statements about probabilities. So it's possible for the conclusions to be wrong. First, if our test result is rejecting a null hypothesis that is actually true, it's called a type 1 error. If our test results in failing to reject a null hypothesis that is actually false, it's called a type 2 error. Now we're ready to put it all together and practice what we learned in this unit.